students, this is Mrs. Dutton, and thank you for tuning in to my video about proofs on triangles. What I've got here for our notes today is just a summary of all the definitions and postulates and theorems that we've learned so far this year that will be helpful in proving that two triangles are congruent. You're currently in a unit about congruent triangles, and it's our task here to build what's called a formal proof, a two-column proof to prove two triangles congruent. So I'm going to give you a little peek at what you're going to be working towards. This is what a two-column proof might look like. A two-column proof gives you a task. It says, given segment AE bisects segment BD, also segment AB is parallel to segment DE, and with that much information, we should be able to prove that the two small triangles in this picture are congruent to one another. Now, in order to do that, we have to know what bisect means, and we have to know what happens to angles when lines are parallel. So it's really pulling from two old previous concepts to build that proof. So what we're going to do first here is we're going to kind of do a little walkthrough, a review of all these different definitions and theorems, and then you should keep this piece of paper handy at all times when you're doing proofs so that you can pull from it. So let's start up here with segments. I tried to break it up by segments and angles and triangles. So when we started our year out, we really talked mostly about segments, trying to find their length, working with it, a little bit of algebra. And here are some things we learned about segments. First, we learned about congruent segments. Okay, so if I have two segments, draw them over here, and I'll call it AB, and then maybe another one here, CD. If I was told that those two segments are congruent, so maybe they have that little congruent segment symbol on it, if I was told that they were congruent segments, what that means is that they are equal in length. Two segments are equal in length if and only if they're congruent. So in a proof, this might look like this. Given AB is congruent to CD, what can we prove? This little 3-dot triangle is the symbol for therefore, or this is what we can prove. If we know they're congruent to one another, that means we also know that they have an equal length. If one segment is 5 centimeters, so is the other. So that's our first little reminder, the definition of congruent segments. If two segments are congruent, then they're equal length, or the other way, if we know their lengths are equal, we know the segments are congruent. Okay, our second example here is about the midpoint theorem. Okay, let's read through that. It says, the midpoint theorem is a point that splits a segment into two congruent segments. All right, which is two segments of equal length. Okay, so draw a little picture again. Here's my segment. Keep it simple. Call it A and B. And I'm going to put M right smack dab in the middle to represent the midpoint. Okay, so if I was told M is the midpoint, then I would automatically know that the two halves are equal. So my proof might look like this. Given M is the midpoint, then I would be able to prove that either I could say the two segments are congruent, or I could say that the two lengths are equal, just depending on what I need it to say. All right, let's check out our next segment definition. Remember a segment bisector? A segment bisector is a lot like a midpoint. Let's read. A segment bisector is a line or a ray that splits a segment into two congruent segments. That's two segments of equal length. So it's almost the exact same as the midpoint theorem. The midpoint theorem is a point that splits the segment. A segment bisector may be something else, like a line or a ray. So check it out. Got my segment. Okay, there's AB again. And then I'm just going to draw in, I don't know, I'll call it line L. Use my little cursive line L. Okay. If I was told line L is a segment bisector, then I would know that it cuts right in the middle. So I'd have to read like this. I'd have to be given the information L is a bisector. And if I was told line L is the bisector, then I would know that the two segments are equal. I'd have to have probably a point there. I'm going to call that point C, I guess. So I would know that AC is congruent to CB, or I would know that AC is equal to CB, depending on what I needed. So you see that segment, bisector, and midpoint theorem are very, very, very similar. Just depends on the words that are used. They're either naming a midpoint or they're naming something that builds a bisector. Okay, our last segment thing to review is the segment addition postulate. And let's read through this one. This one's kind of tricky. If A, B, and C are collinear points, okay, freeze right there. Collinear means on the same line. So it says that A, B, and C are on the same line. So I'm going to start with a line. Then it says B is somewhere between A and C. So it doesn't say that it has to be right in the middle. It does say it's somewhere between. So I'm going to put it off to the side a little. I'm not going to use it as a midpoint because I don't want to get confused with these other things. If all of this is true, if that's how the picture is drawn, then the distance from A to B plus the distance from B to C is equal to the distance all the way from A to, I see a typo, yikes, A to C. Change that for me, that was a mistake. Let's see what that looks like over here. Distance from A to B, so from A all the way to B, plus the distance from B all the way to C, if you have another highlighter, yep, plus the distance from B all the way to C is equal to the distance from A all the way to C, and that'll cover up the whole line. That'll be the entire line. So from A to C is all the way across. That's called the segment addition postulate. I think maybe on IXL they call it like the segment length postulate, perhaps. We call it the segment addition postulate. Okay, so these are the four definitions or theorems you might use when you're working with segments. Next, let's look at some of the definitions and theorems we'll use with angles. There's many more here, so let's take a peek. All right. When we're looking at angles, there's a couple extras. Let's start with the angle addition postulate. It's a lot like the segment addition postulate, but we apply it to angles. Let's read. If B is in the interior of AOC, okay, and that's an angle. If B is somewhere in the interior of angle AOC, so let's start here. Draw an angle AOC, and B is somewhere in the interior, so I'm going to put B over here. All right, then the measure of angle AOB, let me get that measure drawn in. I might call that angle 1, plus the measure of angle BOC, and call that angle 2, is equal to the measure of AOC. It's equal to the entire angle. So step back and think about that. If you have two little angles that are back to back, and you add those two measurements together, they equal the entire angle. So angle AOB, the measure of that angle, plus the measure of its adjacent angle right beside it, BOC, adds up to the full angle, AOC. That is your angle addition postulate. All right, now a few definitions just to remind you here. We've got the definition of a right angle is it's an angle whose sum is 90. Maybe draw yourself a teeny tiny little picture. I'm going to put that little box in there to remind me that it's 90 degrees. So an angle whose sum is 90. Okay, notice that this is just one angle. It's not two angles that add up to 90. It's just one angle whose sum is 90. Okay. Next, definition of perpendicular lines. Okay, now here we're naming an angle versus perpendicular lines are focusing on the two lines. So when I draw a set of perpendicular lines, there we go. That means I need two lines that intersect. This says the definition of perpendicular lines are two lines that intersect at a right angle. So our pictures kind of end up looking the same. In definition of a right angle, we are focusing on the angle measure inside between those two lines. When we're talking about definition of perpendicular lines, we're focused on the lines themselves. Again, this is really going to show up differently based on what's given. If the directions give you angle A, let's say given, angle A is a right angle, then what you could conclude is that the measure of angle A is equal to 90 degrees. Okay? So given angle A is a right angle, then that means we can tell that it's 90 degrees. Whereas this would be a different given. This might say given lines M and N are perpendicular. So therefore, all angles are 90 degrees. Okay? So when told that the lines were perpendicular, then we'll know the angles are 90 degrees. The conclusion is the same. The difference is what's given to you. All right, let's see. Next, we have a little review to remember the difference between complementary versus supplementary. This is something we've been studying all year. You guys are really good at this. Here we have definition of complementary angles, two angles whose sum is 90. Two angles. So you could draw a right angle, but you're going to have to split it somehow. Two angles whose sum is 90. Okay, two angles whose sum is 90. So I'm going to put ones and twos in here and write this out. This would be the measure of angle 1 plus the measure of angle 2 equals 90 degrees. Okay, not just one angle that's equal to 90 degrees, two angles. Definition of supplementary angles is almost exactly the same, except the sum changes. Supplementary angles are two angles whose sum is 180. So we'll need a picture with 180 degrees. So I'm going to start with a line, draw in a linear pair, one obtuse angle, one acute angle, and I can be reminded that now these two angles have a sum of 180 degrees. So how might these show up in a proof? Remember, it's all about what's given versus what you have to prove. So the given could be given angle 1 and angle 2 are complementary. Based on what was told to me in the directions, then I could come up with this assumption. Here, it would have to be different. Maybe given angle 1 and angle 2 are supplementary. Well, this is a giant vocab check. You just need to know that supplementary means they add up to 180 degrees. Okay, there's a few more. These next two we looked at in segment form, but now let's look at them when they deal with angles. We've got definition of congruent angles and definition of an angle bisector. So let's check definition of congruent angles. Two angles are equal in measure if and only if they are congruent. So if you are told that two angles are congruent, then you can assume their measurements are equal. Here's what it would look like in a proof. Given angle A is congruent to angle B. Let's take a look at that. There's angle A over here and angle B right here beside it. If I am told that they are congruent to one another, then I can conclude that their measures are equal to one another. Now I know this seems like it's saying the same thing, and it kind of is. When we're talking about congruence, we're saying that the two objects are the same. When we're talking about equality, we're saying that their measurements are the same. So very slight difference. All right, the last one on the front here is the definition of an angle bisector. And take a look, it's almost the same as congruent angles. An angle bisector is a line or a ray that divides an angle into two congruent angles. That's two angles of equal length. So let's look at what would be given. Here's an angle. Call it ABC. Okay, and if I tell you that this ray, I'm going to call it ray BD, if I tell you this ray is a bisector, I'm giving this to you in the directions, ray BD is a bisector, okay, then we should understand that the word bisector means it cuts the angle in half into two congruent angles. So you could draw in these congruent marks. And we could conclude that angle ABD is congruent to the second angle DBC. Okay, so this is the first set of review material. Again, these are things we've learned all year. We're just putting it on one piece of paper to make it easy to access. Flip over and let's look at a few more. Okay, we have some more angle review up here at the top. I've got the definition of a linear pair, which is next. Let's check that out. A linear pair is a set of adjacent supplementary angles. Maybe a picture would help out. Here's my picture. That's the supplementary part because that's the 180 degrees. Adjacent means they're side by side, so I'm just going to slice this into two angles, angle 1 and angle 2. And I can say that angle 1 and angle 2 are a linear pair. So maybe the picture is what's given to me. Then I can conclude that angle 1 and angle 2 are a linear pair. I'm going to abbreviate that. Are a linear pair. This definition would closely follow up with this postulate. Okay? The linear pair postulate goes one step further. It says, if two angles are a linear pair, then they're supplementary. Okay? If two angles are a linear pair, then they're supplementary. So you would have to be given that the two angles are a linear pair so that you could say that they're supplementary. So the given would need to say angle 1 and angle 2 are a linear pair. And then you could conclude with the measure of angle 1 plus the measure of angle 2 is equal to 180 degrees because they are supplementary. Their measurements add up to 180 degrees. Very slight differences here. Again, definition of vertical angles versus vertical angle theorem, very slight differences. The definition is describing what it is. The theorem is describing what it does. So let's take a look at the definition. The definition of a vertical angle set is two non-adjacent angles formed by intersecting lines. Okay, so let's get a picture of intersecting lines. Okay, I'm going to go with a very simple X. And the vertical angles are the non-adjacent angles, which means they're the ones straight across from each other. I'm going to put a 1 and 2 here. So maybe this is my given. Maybe the given is just a picture. If this is the given, then I can conclude that I have a set of vertical angles. Angle 1 and angle 2 are vertical. Now, what would I do with that information? I would apply the vertical angle theorem. Now that I know they're vertical, I can conclude that vertical angles are congruent. So it's just a change in what's given. Given angle 1 and angle 2 are vertical. Conclusion, angle 1 is congruent to angle 2. Okay, whew. Told you there were a lot of angle things we've learned this year. We've been busy learning. This next chunk on your notes here is a review of all the algebraic properties you covered in Algebra 1. Okay, I'm not going to go through each of them. We are strong at algebra, and I don't really plan to introduce very many proofs that really mix your algebra and geometry together. Okay, so the part that you're probably really going to want to focus in on is this part down here, where we've taken the reflexive property, symmetric property, and transitive property of algebra, and we've extended it to geometry. Really, the reflexive property is a very popular reason in our proof selection, okay? The reflexive property simply says that a line segment is congruent to itself, or that an angle is congruent to itself. Now let me show you some pictures of when we may need that. If you've been working through this series on congruent triangles, you've probably seen this picture a lot, maybe a parallelogram that's been split into two triangles. So we would have segment AB congruent to itself. If I use segment AB on the lower triangle, its measurement is the same as if I would use segment AB on the upper triangle. So that would be an example of when we would say a line segment is congruent to itself. An example of when we might say an angle is congruent to itself might look like this set of triangles. Maybe I've got a set of triangles that are packed into each other. Got one triangle inside of another. And angle A up here is congruent in both triangles. So I've got little triangle here with the measure here at angle A. Well, that angle is going to be the same in the bigger triangle. So that could be an example of when I would need the reflexive property. Okay, if you have any other questions about the symmetric or transitive property, make sure you come see me. I'm kind of just guessing you remember those from Algebra 1 because they were so heavily used. All right, next, I'm going to do a real quick review, rundown of our triangle properties here. Remember, there are 5 ways to decide if two triangles are congruent or not. And I've listed out these 5 ways. Two triangles can be congruent because all 3 sides are congruent. So we may have a picture, just make it very basic. where all three sides of one triangle are congruent to all three sides of another triangle. Side angle side would say that two sides and the included angle are congruent. Maybe that would look something like this. Do maybe some vertical triangles here. One side, two sides, and the included angle. That would be a side angle side setup. Then we've got angle angle side versus angle side angle. These two can be pretty confusing. So if you have questions, make sure you come see me. Angle angle side says there are two angles that are congruent and a side outside of those angles, a non-included side. So that might look something like this. So two angles, there's angle 1, there's angle 2, and we have to pick a side that is not between the two angles. So I'm going to go with this bottom side. That would be a setup for angle angle side. Angle side angle is really similar, except the side has moved. Check it out. You still need two angle pairs, but now the side is connecting the two angles to form this pattern of angle, then side, then angle. And then finally, we have hypotenuse leg. And just due to that word hypotenuse, you know that these need to be right triangles. So I'll start with a picture of some right triangles. Put my little right angle in there. And I can know that these two triangles are congruent if they have the same length hypotenuse and one leg. All right, now that was a super speedy review, but you've been studying that all along, so I think you're good to go there. The main thing I want to say about this is these are always, always, always your 5 options when you are trying to prove triangles congruent. So maybe you have a situation where it says triangle ABC is congruent to triangle DEF, and that's what you're trying to prove. Well, your reason is going to be one of these 5. One of these 5 ways. It depends on how you've built up your proof or what the picture provides. So one of these 5 ways is always going to be the reason for why two triangles are congruent. Now, there's something very special that's got a laundry list of letters here, and this is not a typo. This says CPCTC, which stands for the congruent parts of congruent triangles are congruent. CPCTC. So if you've just been working really hard to prove that two triangles are congruent and you discover that they are, then all of their parts become congruent, even if they are parts that are not marked on the picture. So the proof part might look like this. Maybe you've just discovered or you've been given that triangle ABC is congruent to triangle XYZ. Well, just within this congruent statement, I can now prove that, I'll go with this one. What would angle A be congruent to now, even without a picture? Angle A is in the first position, and so is angle X. So because I know that the two triangles are congruent, that means all corresponding parts are also congruent. All right. Come see me if you have any questions. What I'm going to do with the rest of our videos is I'm going to take our practice sheet. Okay, I'm going to take this sheet that's in the box, and I'm going to make short, quick videos about each proof so that you can just watch the ones you want and not have to watch a big, long video about all of them. Happy studying.